All right, let's look at some examples of applications of constant rate of change. All right, so here we have this spaceship that's flying past Earth with a constant velocity. So constant velocity means he's going the same speed in the same direction all the time. Never changes speed, never changes direction. All right, so the spaceship's flying past Earth with a constant velocity of 30 kilometers per second. Always 30 kilometers every second. All right, so we're looking out there and all of a sudden we detect this spaceship flying by. So 5 seconds after we detect it, it's 90 kilometers past Earth. So we'll say to the right of Earth here. It's 90 kilometers past Earth 5 seconds after we detect it. All right, so question number 1 here says to graph the spaceship's distance past Earth as a function of time after detection. So if I say graph the spaceship's distance as a function of time, what that means is we're going to plug time in as the independent variable. The distance that the spaceship is depends on the time. So we're going to put distance on this axis. Okay, so distance as a function of time. A time in this problem is measured in seconds, and distance is measured in kilometers. So after 5 seconds, so 1, 2, 3, 4, 5, the spaceship was 90 kilometers. So these are measured in 10. So 10, 20, 30, 40, 50, 60, 70, 80, 90. So 90 kilometers, 5 seconds, we will have that point. Let's make a graph of this. So if the spaceship was traveling the same velocity all the time, so every second it goes 30 more kilometers. So at 6 seconds, it would have went 30 more kilometers, so it would now be at 120. 100, 110, 120. So at 6, it would be up here at 120. And it's going that same velocity all the time, so at 5.5 seconds, it would have went 15 kilometers, so it would be about here. Any little time in between we could plug in, so we will be allowed to connect all these dots. And you see the spaceship is doing that. So let's say at 4 seconds, it would have been 30 kilometers behind that, so it would have been at 60. 80, 70, 60. So if I plot that point here, and we see what's happening. We can make a graph of that. At 3 seconds, it would have been at 50, 40, 30. At 2 seconds, it would have been 0. At 1 second, it would have been at negative 30. And then at 0 seconds, it would be at negative 60. And so on. And that should be a straight line, of course. All right, write an equation that gives a spaceship's distance past Earth as a function of time. So what that means is I'm just going to write the equation of this line. Let's call the spaceship's distance, let's call that P for position. So P of T equals mx plus B. And instead of an X here, let's use a T to stand for time. So P of T, and make sure you understand that's not P times T, this is a function. P of T, so P stands for position. So the spaceship's position after so many seconds. Right. What is the slope of our line? The slope would be 30. What's the y-intercept? Well, we've already found the y-intercept by graphing it. It's at negative 60. So our function is P of t is equal to 30t minus 60. All right. If and instead of graphing it and looking at it, we could have found the y-intercept by plugging 0 in for, or excuse me, for using the point that that I told you here, the point 590. So let's do it that way. So suppose I hadn't graphed it and I didn't know this negative 60. Okay, so let's start here. I'm going to use this point that we were told, 590. Okay, so I'm going to put a 90 in for the y, and I'm going to put a 5 in for the t. That's 150, so 90 is equal to 150 plus b. Subtract 150 from both sides, and I get negative 60 is equal to b. So we can find the y-intercept that way. So again, the final answer for our equation is P of t is equal to 30t minus 60. All right, let's think of a couple more questions here about our spaceship. So where was the craft when we initially detected it? Okay, so when we initially detected it, that would have been at time 0. Okay, because our time is measuring time after we detected it. So time 0 is when we initially detected the craft. Right, so time 0 would be our y-intercept, so it would be this point right here, so it would be negative 60. What does negative 60 mean in the context of this problem? So negative 60 is our distance. So if it's negative, that means in this case, in our drawing here, to the left of Earth, so it would be behind Earth. Okay, so it should be 60 miles behind Earth, where I'm drawing over here to the left of Earth. Let's work this out algebraically. So if I want time 0, that's the initial value of our function. So that would be P of 0. So I'm going to plug 0 in for t. I get 30 times 0 minus 60. That'll be 0 minus 60, or negative 60. All right, when you're working out a word problem, you always want to keep your units in here. So negative 60 what? Is that negative 60 seconds, or is that kilometers? It's kilometers. So always, when answering a word problem question, keep your units in the problem. So negative 60 kilometers. And what that means is 60 kilometers behind Earth. Okay. When did the craft pass Earth? Okay. So when did it pass Earth? So if negative distances are to the left of the Earth or behind it, and positive distances are to the right of Earth or in front of it, what distance were you from the Earth as soon as you passed it? Well, your distance would be 0. So what we're hunting for in that case is a distance of 0. So we're trying to find the x-intercept. And we've already got that plotted here. The x-intercept is at 2 seconds. Now let's suppose we didn't have a graph. How would we work it out algebraically? To find the x-intercept, I'm going to plug 0 in for y. So in this equation, I want my distance to be 0. The position is 0. So 0 is equal to 30t minus 60. And I want to solve for time. I want to know what time the distance or the position was 0. So I'm going to add 60 to both sides. Divide both sides by 30. And I get t equals 2. Let me write that the other way around. So t equals 2. This is a word problem, so we always got to keep our units in. 2 what? Is it 2 kilometers or is it 2 seconds? So in this case, that would be seconds. Time is measured in seconds. So the spacecraft passed Earth 2 seconds after we detected it. All right, so a couple more questions here about the spacecraft. The first one, when was the craft 50 miles past the Earth? So I want to know at what time was at 50 miles past Earth. So I'm giving you a position, I'm giving you the distance, and I want to know the time. So I'm going to plug 50 in for my distance. So 50 is equal to 30t minus 60. I'm going to add 60 to both sides. So that'll be 110 is equal to 30t. Divide both sides by 30, and I get t is equal to 11 over 3. 11 over 3, what? That would be seconds. So 11 over 3 seconds. 11 over 3 is 3 and 2/3. 3 will go into 11 3 times. Yeah, with 2 left over. Yeah, so 3 and 2/3 of a second. Let's make sure that makes sense on our graph. So at 3 and 2/3 of a second, right here, my graph was, my distance was 50. Right there. So that makes sense graphically. All right, second question. Where was the craft 1.5 seconds after detection? So in this question, I'm giving you the seconds, and I want to know where it's positioned. So I'm going to plug 1.5 in for t. So I'm going to find p of 1.5. So that'll be 30 times 1.5 minus 60. 30 times 1.5 is 45. 45 minus 60, which will be negative 15. And my units are kilometers. So negative 15 kilometers. What does negative 15 mean in the context of this problem? It means it was to the left of Earth, or behind Earth. So we can say 15 kilometers behind Earth. All right, so here's a problem for you guys to work on. So we got this spaceship that's flying away from Earth with a constant acceleration. Remember, acceleration is change in velocity over change in time. 2 seconds after igniting the engines, the spacecraft was moving 7 miles per second. 5 seconds after it lit the engine, it was moving 19 miles per second. So at this time, it was moving this fast, and at this time, it was moving this fast. So you can see its velocity changes. Okay, so velocity is how fast it changes, or how fast its acceleration is how fast its velocity changes, divided by how, or let me try one more time. The acceleration is how fast the velocity changes. No, let me try another time. Acceleration is the change in velocity divided by the change in time. All right. So what I want you guys to do is graph the spaceship's velocity as a function of seconds after the engines were ignited. Okay. And then secondly, I want you to write the equation for that graph that you just made. So pause the video, work on these problems on your own, then restart the video and we'll go over them together. All right, so on the first one, let's make a graph. All right, the spaceship's velocity as a function of seconds after ignition. So on this axis, I'm going to have seconds, and on this axis, I'm going to have velocity. Okay. At 2 seconds, here's 2. The spaceship was moving 7 miles per second. After 5 seconds, it's about here, it was moving 19 miles per second. The acceleration, or the slope, was constant, so we should have a straight line. or something like that. Right, because since acceleration is change in velocity divided by change in time. Change in y over change in x is the slope. If the slope is constant, we have a straight line. So let me say that again. Acceleration is change in velocity divided by change in time. That's change in y over change in x. That's the slope. The slope is constant, so we should have a straight line. All right, write the equation for the crash velocity as a function of time. So we're going to write the equation of this line. So we will have v of t, so that's my function for velocity, is equal to mx plus b. Instead of x, I'm going to use a t plus b. All right, so we need to know the slope and we need to know the y-intercept. So this point is 5, 19. This point is 2, 7. So the slope of this line would be 19 minus 7 over 5 minus 2. 19 minus 7 is 12. 5 minus 2 is 3. So I get a slope of 4. So I go up 12 over 3. So my slope is 4. So t equal to 4t plus b. All right, so now I need to find the y-intercept. I've got a couple of points I can plug in, so let's use the one with smaller numbers. So I'm going to plug a 7 in for my y and a 2 in for my x. So 7 equals 4 times 2 plus b. 7 equals 8 plus b. So b is equal to -1. So my final answer here, my equation would be v of t is equal to 4t minus 1. Okay. And that makes sense on our graph. If we continue this line down, go through there about -1. Okay, here's 4 more problems for you to think about. So work these out, pause the video, then work these out, restart the video, and we'll go over them together. All right, so what was the ship's initial velocity? So what was the velocity when he first ignited his engines? So initial velocity, that would be times 0. So I'm wanting to know v of 0. So I'm going to plug 0 into our equation, and I get 4 times 0 minus 1 is equal to -1, and we got to put our units. Our units are miles per hour. So -1 miles per hour. All right, that's strange. What does -1 miles per hour mean? Okay, so if positive numbers tell you how fast you're going in one direction, then negative numbers are going to mean how fast you're going in the other direction. So here, -1 just means that the spaceship is moving in the opposite direction. Okay, so it would be going toward Earth. So -1 means it's moving toward Earth. So 1 mile per hour toward Earth. Okay. So in this case, a negative velocity means the spaceship's going toward the Earth. Positive velocities means it's going away from the Earth. So negative velocities, we're going toward the Earth. Positive, we're going away from the Earth. All right, let's think about our graph here. So when he first lit the engines on the spaceship, his velocity started increasing at a constant rate. What about before he lit the engines? We don't really know what was going on before he lit the engines. He might have been just moving at a constant velocity. So in this case, we really probably shouldn't put this part of the graph out here. We should probably really stop it at this point. And because we don't know what was going on really before he lit the engines on this. So that wouldn't increase or wouldn't continue past that point. Alright, let's label that. 1. Alright, when did the ship come to a standstill? Okay, so maybe you didn't get this when you were trying to work it out on your own because you didn't know what the negative velocities meant. But now that you know, if negative velocities means I'm moving toward the Earth, positive means I'm moving away from the Earth. So as I'm coming toward it, then I go away from it. When I change directions, my velocity will be 0. Right, so I'm coming toward, I come to a stop, and then I change direction and go the other way. My velocity will be 0, or I will be at a standstill when my velocity is 0. Okay, so what I need to do is put 0 in for velocity. I'm at a standstill when my velocity is 0. So 0 is equal to 4t minus 1. Add 1 to both sides, divide both sides by 4, and I get t is equal to 1/4 seconds. So at 1/4 of a second, my velocity was 0. So right there's 1/4. So this spaceship was actually moving toward the Earth, and it slowed down, slowed down, slowed down until it came to a stop at 1/4 of a second, and then its velocity increased away from Earth again. Alright, what was the velocity after 6 seconds? So I'm giving you the time, I just want to know the velocity, so I'm going to plug 6 in for t. So v of 6 is equal to 4 times 6 minus 1, which will be 24 minus 1, that will be 23, and my units are miles per, well, I put hour here, seconds over there, miles per second. I'll keep everything the same. This should be seconds. So miles per second. When was the velocity? 10 miles per second. So here I'm giving you the velocity. I want to know the time. So I'm going to put 10 in for the velocity. 4t minus 1. Solve that for t. So add 1 to that. Both sides get 11 divided by 4. And I get t is equal to 11 over 4. And this will be seconds. 11 divided by 4 is 2 3/4. So it should be right in this area. And that's where I get 10 at. So that makes sense.